Okay, picking up more logarithm stuff from algebra. Y equal log base b of x if and only if b to the y equals x. So there is the relationship between logarithms and exponentials. All logarithms and exponentials actually are inverses of each other. That these two statements are equivalent. Y equal log base b of x is equivalent to b to the y equals x. Natural log of e to the x is log base e of x is known as natural log x. Natural logs are just log base e. And then because logarithms and exponentials are inverses of each other, log base a, exponential base a, because logarithms and exponentials are inverses of each other, when I compose them, log base a of a to the x is x, and a raised to log base a of x equals x. And then specifically, because this is going to creep up over and over again, specifically, natural log of e to the x is x, and e raised to the natural log of x is x. Because natural logs, the natural log and the natural exponential functions are inverses of each other. So when I do them both, they cancel. And then I have this down here, right here too. Natural log of e to the x is x, e raised to the natural log of x. Because they are inverses. You should know this. That when those situations creep up, I will expect you to simplify it. Then properties of logarithms that you should have had in algebra, but assuming that people don't remember their algebra as well as they should have, we have the product rule for logs. These are algebraic properties, not calculus properties. These are the standard names for these, so I'm not making stuff up here, but they're algebraic properties, not anything, no relationship whatsoever for the product rule for differentiation, no relationship whatsoever to the quotient rule for differentiation. These are algebraic properties. So the product rule for logs says log base b of pq is log base b plus p log base b of q. That you can break up the product of a log by addition. The quotient rule for logs, log base b of p over q is going to be log base b of p minus log base b of q. That the logarithm of a quotient, the logarithm of a fraction, can be split up by subtraction. The power rule for logs, log base b of p to the r is r log base b of p. Now, important to notice here that r is on just the argument. It is not the same, this is not log base b of p to the r. There's no rule for that. That r is just on the exponent, just on the argument, just on the p. And the last one, the reciprocal rule for logs, log base b of 1 over p equals negative log base b of p. That one's not terribly important, but it's commonly listed when you look up properties of logarithms. Not terribly important because we could figure that out ourselves. That just rewriting that fraction with a negative exponent, we get p to the negative 1, and very specifically, that negative 1 is applying only to the argument, whatever comes after the logarithm, and then my power rule for logs tells me that that exponent can come down in front. So practicing a little more here with logarithms, we'll eventually get to some calculus here. It's going to be a while before we get to some calculus, but we'll get there. Evaluate each of the following. So f of x equals e to the x, evaluate these guys. And so that's going to be e raised to the natural log of 3, and you are just supposed to learn that that is going to be 3. But now, honestly, your calculator is going to know that. Second, natural log will give me the e to an exponent, and then my exponent was natural log of 3. Hit enter. and we get 3. But memorize that e's and natural logs are inverses, so when I apply them both, they undo. So this would be e raised to the natural log of 1 over e to the 7th. Well, the same deal's going on. E's and natural logs cancel. So this would be 1 over e to the 7th, and if you wanted to, e to the negative 7th. Natural logs and e's cancel. It's almost the same idea. Now, nothing cancels right yet. Each one of these where we quote-unquote canceled, and we're not canceling, we're just using the property that e's and natural logs are inverses. But notice the e's and natural log were touching. And in that case, I just get the argument of the natural log. Same thing here. The e and the natural log, quote-unquote, are touching. In that case, I just get in this, the 1 over e to the 7th. Here, they're not touching. But I can rewrite this. I'm going to use the log base b of p to the r is r log base p. But backwards. So if I use it backwards, that tells me that that coefficient can come up and become an exponent. And so this becomes e raised to the natural log of 4 squared. That coefficient can come up and become an exponent, because that's what my power rule for logarithm says. And you can use it in whatever order makes sense. Here, quote unquote, the backwards order makes sense, that exponent can go up and become an exponent. And so now my e's and natural log, quote unquote, are touching, so I get 4 squared, or 16. Practicing some more. Just going the other way around now, f of x equal the natural log of x. So now I get natural log of e to the cubed. That natural log and that e, so to speak, are touching. They're composed with each other, so I get 3. Here, this would be the natural log of the square root of e. So one answer right away, square root of e. That's wrong. I just lost my train of thought. So that's the natural log of the square root of e, which is the natural log of e to the 1/2, because I need the e and the natural log touching, and I had that square root in there, so they weren't touching. Now they are touching. I just lost my complete train of thought here. Now they are touching, and so we get 1/2. Natural logs and e's are inverse functions. When they have them both, they quote unquote cancel, or you use the inverse property and get 1/2. There's one way you could do it. We could have also done it this way. That is the natural log of e to the 1/2, just like before. But then our properties of logarithms, that 1/2 could come down in front. You can't see what I'm writing there. So here's an alternate way of doing it. So here's the first way, natural logs and e's cancel, so I get the 1/2. Or here's the second way. Now I have e raised to the 1/2. My power rule of logarithms, that can come down in front and become a coefficient. Then we can memorize, and should memorize, the natural log of e is 1. And I get 1/2. And the last one here, that's going to be the natural log of e raised to the 3 natural log of 2. Just plug it in there. And so natural log and e, inverses, so that's going to be 3 natural log of 2, which is a perfectly good and fine answer, but that almost assuredly is not the answer that the computer would want. That it's probably going to do that exponent or that coefficient in front can come up and become an exponent, and we get the natural log of 8. I'm bothered again by that. Yeah, that's fine. I was thinking about doing it another way, and I would get the same answer the other way, so I'm all cool with that. Here's the other way I was thinking about doing it. Since I'm, sit there, long pause, and you were sitting there watching the video, what the hell was she doing? Here's another way that I was thinking about it. So we'll go up here. So f e raised to the 3 natural log of 2. I could have said that that was f e to the natural log of 2 cubed. Bringing that coefficient up to the top, which would give me f of e natural log of 8. Well, e and the natural log, those are touching. So that'd be f of 8. Then apply the logarithm, and I get natural log of 8. So there would be another way of doing it. I don't think this is the easier way to do it. I think what I did here was the easier way. But here would be another way of doing it. That 3 can go up and become an exponent. So then I have natural log of 8. Then my e and my natural log inverses, they're touching, so I just get the 8. Then apply the function, that the function was the natural log of x. So plug in 8 for x, and I get natural log of 8. And there's my answer once again. So frequently, there's going to be more than one way to do these things. Okay, use the properties of logarithms to expand the logarithmic expression as much as possible. Evaluate the logarithmic expression without a calculator as much as possible. And so the idea here is to pull this apart using our properties of logarithms, these properties over here. So I start with the whole thing, and then using the quotient rule, for logs, we would get that this is the natural log of x to the 1/3 e to the 4th minus the natural log of 6 times x minus 4 quantity squared. That the quotient rule for logs says I can pull apart a fraction by subtraction. So there's the first step. Second step, now using product rule for logs, the product rule of logs says that products can be split up by addition. Notice the careful use of parentheses on the second one because I want to split it up, but I want that minus sign to apply to the entire result. Then the power rule for logs tells me that all those exponents can come down in front, and I'll distribute that minus sign along the way. And then I have one last thing I can do here. Natural log of e is 1, and so I get 1/3 natural log of x plus 4 minus natural log of x minus 2 natural log of x minus 4. And there we've done what they asked us to do, to expand it as much as possible. Now, why we'd want to do this? Calculus on this expression, really, really hard and awful. Calculus on this expression, really, really easy. Derivative hard here, awful, derivative easy. And then please note on the end, there was no way to simplify the natural log of x minus 4. There isn't a property about logarithms where you have adding or subtracting in the logarithm. And that's the end of this lecture.